Alright, let's start. Till now, we talked about translation. The rotation is pretty easy. We just have to copy-paste all the things we learned in translation. You know, in translation, we have like xt, vxt, acceleration, we have an x-axis, origin, unit. How does it look like in rotation? The origin is technically here. Instead of xt, we have theta t, angular displacement. Instead of velocity, we have angular velocity, and instead of acceleration, we have angular acceleration, which is depending on the book. Sometimes it's alpha, sometimes it's beta. Let's use the beta here. What is angular displacement? So if this is theta equal 0, when you move the theta, t is the angle on the circle. You know the first circle is 2 pi. So let's radians and degree. So for example, 90 degree is pi over 2, 180 is pi, 360 is 2 pi. This is the full circle. So when I go from here to here, this is pi over 2. If I go further till here, this is the pi, and the full rotation is 2 pi. Just double check, do you hear me? I suppose yes. We need some other information like period time. This is the time we need to take a full circle, and the frequency, thanks. Frequency is 1 over period time. These are common values I think you are familiar with. How to calculate? I create a picture about this screen and delete the table. So, what did we do in translation? In translation, we have to say where is the body, for example, at 1 meter, at t equals 0, what is the speed at t equals 0, and what is the acceleration. Let's say it's 10 meters per square. This is the constant acceleration in translation. How does it look like for rotation? The boundary condition, where is the body in angular displacement? So it means pi. What is the angular velocity at t equals 0? This is pi over 4. Its unit is 1 over s. And what is the angular acceleration? This is pi over 2. 1 over s squared. How does it look like? Always we start with a coordinate system. In this case, coordinate system is pretty simple, a circle, plus we have to say where is the origin, where is the theta equal 0. What does it mean at t equal 0 second I'm at pi? It means I'm here. This is the pi. So this is where I am at the beginning of the motion. There is an initial angular velocity. That means here I have an omega, t equals 0 is pi over 4, 1 over s. What does it pi over 4, 1 over s means? If there is No acceleration, only a constant angular velocity. In every second, I will move pi over 4. What is pi over 4? Pi over 4 is 45 degree. So for example, this is 1 second. At 2 seconds I'm here. No, this is 0 second. At 1 second I'm here. At 2 seconds I'm here. At 3 seconds I'm here. At 4 seconds I'm here. And so on and so on. So in the case of beta equals 0, this is how I move. But in this case, there is an angular acceleration. How can I calculate it? Similar what we did for translation. So the change, the delta of the angular velocity is the integral from 0 from the initial to t. This is, the beta. Angular acceleration is the integral of the angular velocity is the integral of angular acceleration. That's 0 t pi over 2, which is the primitive function is pi over 2t from 0 to t. Since at 0 this is 0, this is pi over 2t. What is omega t? Omega t is the omega at t equals 0, so here, plus the changes of the omega, which is, since at t equals 0, my initial angular velocity is p over 4 plus p over 2t. What is the angular displacement? Angular displacement is the integral of the angular velocity. This is 0 to t. Let me start with the linear term p over 4, which is pi over 4t squared. You know, the primitive function for t is 1 over 2t squared, so the primitive function is pi over 2t is a pi over 4t squared, plus pi over 4t from 0 to t. What is the angular displacement? My initial position, which is pi, plus the change. So that's pi over 4t squared plus pi over 4t plus the initial position is pi. So if I know the initial angular position, the initial angular velocity, and the constant angular acceleration, very similar to the translation, you can calculate how the particle moves on the circle. If I want to ask why is the body at t equals 0, 1, 5, 10, you can calculate just writing 0, 1, 5, and 10 instead of t. And let's calculate. So at t equals 0, this is pi, since the t squared and also the t 0. At t equals 1, this is pi over 4 times 1 squared, which is 1, plus pi over 4 times 1 plus pi. This is 3 times pi over 2, which is here. What if I'm at t equals 5 seconds? This is 17 pi over 2. So we know 2 pi let's calculate it for full circle. So how 17 pi over 2 looks like? This is the theta equals 0, this is the origin. This is where I am at t equals 0 second. At t equals 1 second, I'm here. This is 3 pi over 2. And at 5 seconds, 17 pi over 2, theta t equal 5 seconds is 17 pi over 2. Let's calculate n in the form of n times 2 pi plus something. So this is 16 pi over 2 plus pi over 2. The 16 pi over 2 is 8 pi plus pi over 2, which is 4 times 2 pi plus pi over 2. So I know I'm somewhere here at pi over 2, but after 4 full circle. So means at t equals 0 I'm here, then t equals 1, and then I will pass the origin 1 times, 2 times, 3 times, 4 times, full circle, and then I will be here at pi over 2. Similar at, so this is the first, this is the second, third, and after going through the theta equals 0 line, at t equals 5 seconds, I'm at the pi over 2 position. Alright, few things you should know. So technically the acceleration is the change of the velocity. Even at the constant circular motion, the speed is the same, but the velocity, the vector, is changed. You can see here, so even the v at t plus delta t is the same, but since it changed its direction, there is a delta v, and the delta v over delta t is the acceleration that's a non-null value even at constant speed or constant circular velocity. And there is another fact, another formula you should remember. This is the angular acceleration. So this is the acceleration you need to keep a body on a circular path with a radius r with the constant v acceleration. So this is the constant angular velocity at constant speed, and for that you need a angular acceleration v over 2 v over 2 over r to keep the body on this circular path. Let's calculate something. So let's consider there is a ball with the mass m, and there is a constant speed in a horizontal circular path. You can play that game. According to Newton's first law, so the ball should move in a straight line, but however, it moves in a circular path. What is the force? What you need for that? This is the angular acceleration times mass. So this is the mv2 over r. What if the string breaks? The ball will move along the straight line path. This is a tangent of the circle. So anytime you move a body on a circular path, you will need this centripetal force to keep the constant angular velocity. One example, so for example, you move with your car and there is a curvature on the road. The radius of the curve is 35 meters and the static friction is 0.5. Let's suppose the street is dry enough. The 0.5 is pretty common. Technically, between the wheel and the road, it's from 0.5 to 1, depending on the of the surface of the road or the material of your wheels. So what is the maximum speed you can make the turn successfully? The static friction will be the centripetal force. You know the static friction has a maximum value. Its maximum value is mu times the the perpendicular force, which is the mass. We also know what is the formula for centripetal force. And if you combine these two formulas, you can have a maximum value to make this turn successfully, which is 13 meters. You can imagine when the road is wet, this 0.5 will be, for example, 0.2 or 0.3. You can't make this turn successfully with 13 meters per second, but instead only, let's say, 5 meters per second. And also something, if you also accelerate your car during you make this turn, that means the static friction will be shared between the centripetal force and the acceleration. That means the speed you can reach to make the turn successfully can be less. Alright, let's talk a bit about systems. System can be one particle, one body. Till now we mainly talked about one body motion, even if it's translational or rotational. It can be a collection of bodies, let's say your room. It can be a volume, let's again your room where you are sitting now. It can vary its size and shape, like a bowl or something, but all of the system, I mean, for every system, it should be true that the system has a boundary that divides the universe to system and environment. And we not only identify what is a system, like a couple of bodies, like chairs, tables, laptops, and so on, but it's also, we have to identify what is the interaction between the system and the environment. Why is it important? Because if we want to talk about work, the work is technically the capital W. It's done on a system by or a constant or not constant force by the environment. How does it look like? So for example, here you have this box and there is a external F force. The work is the scalar product of the vector F times the displacement. You remember the vectorial product. This is the magnitude of the vector of vectors. So you multiply the magnitude of the vectors times cosinus alpha, which is the angle between the force and the displacement. So there is a system, in this case this is the box, and if there is an external force that comes from the environment, and if the body moves from the position 1 to position 2 and the displacement is delta r, the work done by the environment on this body will be F times delta r. If the S is constant, this is F delta r times cosine of theta. Let's see some examples. So look at the picture. In the case of A, the F times delta x is 0 since they are perpendicular, and cosinus 90 is 0. If there is a delta x on your right and the force is on point to the left, this is still a valid work. It's work, but this work will be negative. So that means the work done by the external environment on this body is a negative. We will see what does it mean negative work. In this case of 60 and opposite direction, this is the negative, but F times delta x times cosinus 60, and of course in the case of D you have to multiply, in this case again with 60, since the angle between the delta x and the f is 16 because the perpendicular direction of the x and the f has the difference in angle like 30. So we can calculate it if we know what is the force like 1 Newton, what is the delta x like 1 meter. If the angle is, for example, 0, this is 1 joule. If the force is not a constant, you can create the force displacement function. So let's see, the F here is 10 Newton, but here it will be smaller and here it will be larger again. So the work is technically the area under the fx function, which is the integral from, in this case, 0 to, let's say, 1 meter from the initial x, or let's say this is the initial, this is the final position, fx dx. So the work is a path integral of the force. You can imagine this situation in 3D. In this case, this is again a path integral, but in 3D, calculating this path integral is not that easy because it's three-dimensional integral. I mentioned before that there are not only one-dimensional integral, there are also two- and three-dimensional. It's just a question of your math skills, whether you can solve it. Let's say the simplest force we can imagine, which is not a constant form, this is the force of the spring. There is a so-called Hooke's law that the force on a spring, let's say this is the spring in equilibrium, and if you push the spring, that means, and let it move, that means you will move that direction, and the force, so this is the 0, here we are at minus x, the force is minus x d, that means this minus here means if you push the spring, you move that direction, but the force will be opposite to it. So the force is always opposite of your distance from the equilibrium. And if you calculate this, oh, I need more space. If you calculate this F equal minus x d from this minus x, this is the minus x, this is the 0. The area of this triangle is 1 over 2 dx squared. And this is the work done by the spring moving from here, from A to B. Alright, let's go back to Newton's second law, and you can see, you look at this equation here, so the work is the force along its displacement. So if instead of force we write max, this is a one-dimensional motion, and you can do this derivation, at the end you will get that the force is something that changes this something, 1 over 2 mv squared. We know this is the kinetic energy, but here this is just one formula. So the work is something that changes this 1 over 2 mv squared. So if you calculate the difference 1 over mv final square minus 1 over 2 mv initial square, this is something like work. Why is it important? Because you can name it like kinetic energy, and you can say that if an external force can only change the speed or velocity of the body, the work will be transformed to the change of the kinetic energy. This is the work theorem. So the work done by the net forces is equals to the change of kinetic energy. This is what we use several times. So in this case, you do not have to solve the motion of the equations, because if you know the force, let's say 10 joule, you know, and if you know the initial speed, which is normally we know, you can know the final speed. Don't forget, you don't know where is the body, you only know what is the changes of kinetic energy. So you can't say where is the body, but you can say its kinetic energy, or since the kinetic energy depends only on the speed, you can tell the speed. Let's say some example for the kinetic energies. This is also something we have to write in normal form, since you can imagine the kinetic energy of one oxygen molecule in your air, in the air you are sitting. This is 10 to minus 21, and for example, the Earth's kinetic energy around the Sun is something which is 10 to 33, and we didn't mention the kinetic energy of the galaxy or kinetic energy of the universe, which is, let's say, 10 to 80 or something. Alright, let's see an example. So here we have a body with 5 kilograms, and you will move this body with the force, how can I write it, with the force like this. And it will move, delta x is 50 meter, and the F is 100 Newton, and the angle is 30. Let's calculate the frictionless. Of course, I have to divide again the F into, let's say this is the X and this is the Y. The Fx equal F times cosinus 30, which is let's say 87 Newton, and the Fy is 50 Newton. We also have the weight, which is 50 Newton again. How will it move? Since there is no friction, we only have to integrate the Fx from 0 to 50, which is 0 to 50, the 78 constant force, that's 78 T, 0, 50, this is 50 times 78 joule. If the initial speed was 0, since the weight, the work done by this external F force will change the kinetic energy. If the initial was 0, this part is 0, so this 50 times 87 will go into the kinetic energy of the body. More interesting is when the friction equals 0.2, because the kinetic friction will be mu times the perpendicular forces. In this case, the mu times not only the rate, but also the perpendicular component of the external forces, or external force, which is 0.2 times 50 plus 50. That's 100, that's 20. So, and you remember the work is the net force along x. In this case, the net force is, so this is the positive direction, this 87 minus 20 from 0 to 50. In this case, 0 to 50, 67. If you do this calculation, there will be 67 times 50. So this is the work done by this external force plus done by the friction, which is, you see, so this is the positive direction. The work done by the friction technically is always negative, since the direction of the friction is opposite to the direction of the motion. I think you will be able to solve such an example, and for homework you can look at this YouTube video, click on this 12 and do some assumptions, and in the here you can find some numbers like what is the weight of the train, what is the maximum speed of the train, and by the definition of the work you can calculate what is the force done by Spider-Man, and believe or not, you will get some really reliable numbers. What is the force you need to break the sleepers as in the sea? We will solve it on the seminar. Alright, I think that's all. Any questions? Don't forget, we will write tests during the seminar, so don't forget to come and try to check my last YouTube videos for the way how we should calculate things. And you know, you can save the screenshots from this smart cup if you want to check again what I wrote there. If there is no more questions, I finish here and let's meet on the seminars. Bye.